Hi guys, welcome back. So today's topic is the introduction to a limit. So what is a limit? The idea of a limit is as a function approaches a certain value, let's call it a, what does it do? What's its behavior? So limits don't depend on the actual value of the function at that particular point. They care about the behavior of the function. So is it skyrocketing off to infinity? Is it a hole there? Like what's happening? And so really the main idea with this is we don't care what's actually happening at the value, we care what's happening around it. Okay, so why do we care about limits? Besides them being a fundamental topic of calculus that we just need to study, limits are important because for some functions we don't or we can't know the value of every single point along the function. And so we use limits to predict how the function will behave at a certain point. Okay, so now I'm going to write some limit notation just so we can get familiar with how a limit actually looks. Okay, so limit notation. Okay, so you'll see this definitely in your textbooks or on your tests or something like that. But this is how, just the basic limit looks. And it's pronounced like the limit as x approaches a of f of x. Okay, so now I'm gonna leave that. Actually, no, I'm not. I'm gonna erase that and show you guys some quick examples. So, one. Okie dokie. So this is going to be an example of a rational function. Let's say it's y is equal to 1 over x minus 2. And this is the value a that we care about. This will be 2. Okay, so I'm going to ask what's the limit as x approaches a of f of x? Okay, and then let's say this right here is like 5. I know. So let's say it's like 5. Okay, so what we do when we are looking for the value of a limit, these examples are just to give us kind of an intuitive understanding of what a limit is. And so we look at the function, how is it behaving? Okay, so as we approach from the top side, it looks like the value is just close to 5. And as we approach from this side, it kind of just goes off to infinity. So we can pretty safely say that the limit as x approaches a of f of x, in this case, is equal to 5. Okie dokie. I'm going to give another example. This time it'll be y is equal to x plus 3. 3. And make it kind of special, we have a hole there. Okay, and so the hole will be our value at a. Let's say this is like 10, I don't know. Okay, so again we're going to ask, what is the limit as x approaches a of f of x? Okay, so you'll notice this time it's a little bit different. The function isn't actually defined at the value a that we care about. But that's okay because the limit, again, doesn't depend on what the actual value is at that certain place. It just cares about like the behavior, what's happening. Is it approaching a certain value? So in this case, we can see, okay, so we go along up this way. It looks like it's pretty close to 10. We come down from the top. It also looks like it's going to 10. It doesn't matter that the actual function isn't defined at that value. There's a hole there, but that's okay because it looks like the function is approaching from both sides 10. So we can pretty safely say that the limit as x approaches a of f of x is equal to 10. Okay, now I'm just going to give one last example. Then we'll just get some more notation and solid definitions for this. Okie dokie, so I'm going to draw a trig function there, and let's say this is pi over 2, and this is a. So you'll notice right away with this one, I didn't define what the function was, and that's okay. For some functions, you're not going to know what their exact equation is, but you're going to still be asked to find what the limit as x approaches a of f of x is for that particular function. So again, I'm going to ask, what's the limit as x approaches a of f of x? Okay, so from this one, we can we go along the left side, looks like it's approaching pi over 2. From the right side, looks like it's approaching pi over 2, so we can say that the limit as x approaches a of f of x is equal to pi over 2 for this function. Okie dokie. Okay, so now I'm going to give a formal definition of a limit. Now that we've kind of gotten a more intuitive understanding of what a limit is, now it's a good time to define it. Okay, so to say that the limit as x approaches a of f of x is L means that, okay, so the limit of f of x as x approaches a is L if the value of f of x is as close as we want to L for all x sufficiently close but not equal to a. Okay, so this is the formal definition, kind of the wordy version of what a limit actually is. So before, with the examples I gave, we were trying to get an intuitive understanding of what does a limit mean? What does it feel like when we ask what the limit as x approaches a of f of x of a particular function is? And what does it mean when we say it's equal to some finite value, and it's usually just called L? And to say that the limit as f of x as x approaches a is L if the value of f of x is as close as we want to L for all x sufficiently close but not equal to a. What does that mean? It's saying that as we get closer and closer to the value that we're looking at, how is the function behaving? And to say that it equals L means we want it to be just as close as we want to L. But with all things in math, close enough and near and things like that you might see in your textbook aren't precise mathematically, which brings us to the discussion of epsilon delta definition of a limit. Okay, so the epsilon Okay, so epsilon and delta are just Greek symbols that represent arbitrarily small positive numbers. So they're really just really tiny, small positive numbers. Okay, so the absolute value of f of x minus L is less than epsilon. The distance between f of x and L is less than epsilon. Epsilon is greater than 0. Delta is greater than 0, such that 0 is less than the absolute value of x minus a less than delta, then the absolute value of f of x minus L is less than epsilon. Okay, so we have epsilon, we have delta, and we have these two statements. So we have the absolute value of f of x minus L is less than epsilon, and then we have 0 is less than the absolute value of x minus a, which is less than delta. Okay, so this boils down to, as x gets closer and closer to a, f of x also continues to get closer and stay closer to L. So what it's saying is the absolute value of the f of x minus what we're saying that the limit is equal to, which is L, has to be less than epsilon. And epsilon is just that really, really small, tiny, arbitrarily positive number. And it's basically what these statements are saying is that we want a really close, precise mathematical value for the close enough or near enough statements that we said earlier, which is just what the epsilon and the delta serve to do. So hopefully that gives you a bit more mathematical kind of wherewithal to understand what these limits are actually saying. Okie dokie. So now we're going to do another example, and I'm going to say that y is equal to x squared, and then I'm going to ask, what's the limit as x approaches 3 of f of x? And then similarly, I'm just going to, you might see, or limit as x approaches 3 of x squared. It's the same thing, but you might just see it written differently. So I just want to give you both separate notations for that. Okay, so I'm going to draw this function on the board. And then I'm going to draw these two arrows as well. Okay, so remember what we're asking when we're asking what a limit is. We're really asking, as x gets closer and closer to 3, what is the function doing? Is it approaching a certain value? Is there a hole? Is there a point elsewhere? Like, what's happening? And keep in mind, we're observing the behavior of the function. We don't actually care what the actual function's value is at that point. Okay, so the arrows that I drew are representing the left-hand and the right-hand limits. So, we already did this before in kind of an intuitive sense, but I wanted to give some, actual definitions for what these are. Okay, so the left-hand arrow represents what's happening as x approaches 3 from the negative side, which is the one up top, and then the right arrow represents what's happening as x approaches 3 from the right side, which is this bottom arrow. Okay, so this is the general notation. So left hand, and you'll see abbreviations with like LH, and that just stands for left hand. So that is the limit from the left as x approaches a, x less than a, close to a. And then similarly, this is the right hand, abbreviated with the RH, and it is the limit from the right as x approaches a, all x greater than, close to a. And oops, this was I wanted the actual, so the limit as x approaches a from the positive side of f of x is equal to L, and then the limit as x approaches a from the left side of f of x is equal to L. Okay, so remember how we said the limit as x approaches a just generally of f of x is equal to L? Well, these are the components that break down what the limit as x approaches f of x is. So it's the limit as x approaches a from the left side, and then the limit as x approaches a of f of x from the right side. Okie dokie. So I'm going to erase a little bit. I'm going to rewrite those limits that I had before. Okay, so back to the example. The limit as x approaches 3 from the negative side of x squared. And then the limit as x approaches 3 from the positive side of x squared. So when we ask the limit as x approaches 3 from f of x, we really do have to ask both of these. Okay, so if we follow the left arrow, as we approach 3 from the left side, as x approaches 3 from the left side, it looks like it's going to 9. So we can say that the limit as x approaches 3 from the negative side of x squared is equal to 9. And then as we follow the right arrow coming from above, it also looks like it's approaching 9. So we can say the limit as x approaches 3 from the positive side of x squared is equal to 9. And so because both of these converge to the same number, which means they just equal the same finite value, we can say that the limit as x approaches 3 of f of x is equal to 9. And that would be like our final answer. Okay, so in summary, when the left and right hand limits equal and exist to the same number, that means that the limit exists to L. But when the left hand and the right hand limits don't equal the same number, that means the limit does not exist. So I'm going to give you a quick example of what happens when the limit actually doesn't exist. And in all the examples we've had previously, they've actually existed, but that's not always the case. Okay, so let's say this is like 10, let's say this is 2. So we're going to ask the limit as x approaches a, but remember, in order to figure out of f of x equals question mark, and remember to actually ask what this limit is equal to, we need to do the left-hand limits and the right-hand limits. So we're going to do the limit as x approaches a from the negative side of f of x, and as we go up from the left side, it actually looks like it equals to 10. We can say it's equal to 10. And then the limit as x approaches a from the positive side of f of x. And as we come down, there's a hole, but remember, we don't actually care what it is at that value. It just looks like it's approaching 2. So we can say that's approaching 2. Okay, so we have the limit from the left-hand side. We have the limit from the right-hand side. Last time I checked, 2 is not equal to 10, and because these two numbers are not the same, the limit does not exist. So in order to answer our question, we would say the limit as x approaches a of f of x does not exist. And that's also abbreviated by D and E. So if you see me write D and E, it just means that limit does not exist. And a good thing to point out right now, when you don't see this little negative sign or the positive sign denoting the particular left hand and the right hand limits, if it's just nothing right there, that means you have to do both of them to figure out what the actual limit as x approaches a of f of x equals. Because remember, the left hand limits and the right hand limits both have to exist and equal the same value for the limit to converge to a finite value. Okay, so this last thing we're going to do is evaluate with tables. I'm just going to give you a quick example of how you would evaluate a certain limit with tables. Okay, sweet. So I just finished writing the table, and so now I'm going to give you the actual question that we're looking for. So the limit as x approaches 5 of f of x. Okay, so when we look at this table, we notice a couple things. First, it doesn't actually tell us what f of x is. And remember I said earlier, they don't always tell you what the actual function is that you're trying to evaluate the limit for. Sometimes they might just give you a table and then just expect you to know and be able to evaluate correctly what the limit is. Okay, so we have the limit as x approaches 5. So we have 4.9, 4.9, 4.999, and it gets closer and closer, and then 5, we don't actually know what happens at 5. And then we have 6.001, 6.01, 6.1, and it continues. And then for the actual function values, we have 11.25, 11.01, 11.0001, and then more question marks, and then 10.999, 10.9, etc. Okay, so when we're looking at this table, we can infer a couple of things. The numbers are steadily decreasing. So we start at 11.25, we end at 10.75. And so when we're marching along these f of x values, it looks like it's getting really, really, really close to, but never quite ends up being 11. And so it's the same thing when we're looking at the x values. It doesn't really get to the 5, because sometimes you're just going to get a table and you're not going to actually know what the specific value for that function is. You're going to have to infer what the behavior of the function is telling you that value should be really, really close to. And so this is really a good example to illustrate what the idea of a limit is. We don't care what's happening at that value. We care about the behavior of the function. And the behavior of the function is telling us that value is really, really close to 11. So if we're going to rewrite this question really fast, the limit is x approaches 5 of f of x. Based on what the graph is telling us, I would say that equals 11. And so we can just, box this answer, whatever. So hopefully you guys learned some things about what limits are and how we can interpret them intuitively, as well as getting a good mathematical definition for them. In the next video, I'm going to cover way more about limit laws, evaluating limits. But as always, if you guys have questions, make sure to leave them down below in the comments, and I will answer them as soon as possible. Thank you.